Hello there, guys. Hope you're all well. Today we're going to have the fourth video in the series of network fundamentals around layer 3 routing. What it is, some kind of fundamentals on layer 3 routing, and then also some insight into static versus dynamic, and what that actually means for us when we're forwarding our traffic. So, why is it not advancing? There we go. So really high level, what is routing? What is layer 3 routing? Why do we need it? Well, routing is all about forwarding those traffics from that traffic from one local destination to a remote destination. That is all based on your IPs that you set in those bits of traffic that you're sending across the network. And that can be, a scope of, a small office network from your laptop to a server that's in a server room somewhere, or that could be from, your laptop to, a BBC server somewhere sitting across the internet that is hosting the BBC webpage, for example. Two very different traffic flows, but both are relying most likely on IP routing. And so if you remember back to the OSI model that we talked about, we're only sitting at that layer 3 information. We only really need to read the IP information to be able to forward the traffic at a very basic level. Routers will and can inspect those higher layers to do some more advanced features like load balancing. But otherwise, mainly how a router works is it will look at that L3 or layer 3 information and make a decision. Now that decision is usually done hop by hop. So we are going between, well, I'll bring up a diagram. If we are moving from R6, ignore all this information here, but if we're moving from R6 and we want to go towards R1, R6 makes a decision based on its view of the network, its routing table. We'll get onto what this all means a little bit later on. R6 will then forward the traffic out of whatever path it deems appropriate. The next host or next router in the path will then make its decision, and so on and so forth, till you get to the relevant end destination. And that's the concept of routing. So hop by hop, we're making a decision based on the network state or the routing information that we have available to us as the local router. So how do we do that? Well, at a high level, we rely on that subnet information that we talked about in the last talk. So we have that concept of a network portion and a end. So in the last talk, we have that concept of a subnet or a subnet mask or a subnet, effectively. And that is breaking up an IP address into a network portion and then a end host portion. So we have a network portion which effectively identifies a group of end hosts. So if I find the relevant slide with the relevant details, wherever it is, that are referenced in here, this is a really quick example that we went through in the previous talk. And this is an example of a /18, which has a big range of this end host portion. In the case of a /18, it gives you 16,000 possible end hosts or IP addresses, or around that number, basically. If that was, let's say, a /24, and we only had 8 bits to represent those end hosts, then that would give us around 250 possible end host IPs, which is more specific, and it's more known. You're less likely to hit the wrong path or go down the wrong route to find the actual end destination. You've got 150 possible IPs in that direction if your routing information is correct. So one function of routing, if I go all the way back here, is that we're looking for that most specific network segment in our routing information, in our routing table, to say, well, that's the most specific, we want to go in that direction. So as we hop across a layer 3 domain, in the case of this, let's say we are on R6. We have routes that point towards the internet, which are what's called a default route, and that'll match against anything. But in this situation, we're moving from this subnet to this subnet up here, very specific /24 range. We also have a /16, which is a little bit wider, but it's more specific than just anything, which is the default route. We then also have that more specific /24 route that we can also match on. And as a result, what the router is going to do is it's actually going to match for that more specific routing entry and then select that. Anyway, going a little bit too far right now. We'll touch on that a little bit later. But yeah, you can also then imagine this routing concept as very similar to how Google Maps or sat-navs will work. They'll have an understanding of the road system in the case of Google Maps, and they'll be able to plot out the best path between your source and your destination. Or that could be your home and the office for a morning commute, pre-COVID, obviously. And so it will decide based on traffic conditions and the actual roads, which is the fastest path based on maybe historic data, maybe based on any accidents, any roadworks, those kind of things, and actually the speeds of those roads. And routing is very, very, very similar to the way that something like SatNav and Google Maps directions would work. You have a range of network paths that you can take to get from source to destination. And with that, you can then decide the relevant path that you're going to take, the best path. And that, in essence, is what layer 3 routing is all about. It's choosing the relevant best path based on a range of different variables. So that's the most specific segment and the shortest path based on some kind of metric. So that's a really high level for you. Skipping over these. We then obviously have to look at how do we implement that actual routing information? Well, you've got two very generic options. One is static routing and one is dynamic routing. As the name suggests, static is static, it is fixed. What that means is usually you will have some kind of network administrator who will log onto the device, log onto the CLI or the GUI, depending on the device, and manually install some kind of routing information to say, this traffic should go out of this specific interface towards this specific device. And that's great in some situations. If you've got a very fixed network, a very small network, that can work wonders, and that can work perfectly fine. If your network isn't going to change or it's very static, it's not dynamic in any sense. Perfect example of this is a very simple office network. If you don't have test devices or you don't have like a lab environment and it's just computers, a few offices, those kind of things, then a static network can work perfectly for these kind of things. But obviously, any link failures, any congestion, any network additions or changes that you need to make have to go through a very rigorous process to understand the existing topology and make sure that you're installing static routes that make sense. If you had a wide topology, well, then you've got to know that wide topology in very, very detailed in very detailed ways to make sure that your static routes on one point of the network, so your static routes in R6, for example, point towards R4, and if they point towards then R3, you want to make sure that actually R3 has the static route to point in the right direction towards that specific destination. If R3 had just a default route pointing all the way back to R6 through R5, well, if we've got traffic sending up towards R3 and it doesn't have forwarding path other than a default route, it's then going to start getting stuck. It's just a very quick example of why sometimes those static routes can be a pain and they can be an administration overhead, basically. Also means that whenever you're adding something to a network, well, that's going to take some time to process, to plan, and make sure that it's properly implemented. In contrast, you have things like dynamic protocols, which allow you to
very quickly set up the network and set up routing information. Typically, it's just identify your neighbors or identify the interfaces that you want to include in the protocol. The network devices will automatically identify its neighbors and gain network state based on either their local information or their neighbors' information or some kind of global network state that is shared around the devices. That process really does depend on what protocol you are running under the hood. So in some cases, it'll be one method. In some cases, it'll be a different method. But obviously, the concepts of those dynamic protocols are very consistent. So, you know, if you have a change in the available paths, whether that be maybe bandwidth, maybe that be a link goes down or anything in between, you know, the routing protocols should be intelligent enough to be able to see that change in state, process that change in state, and understand what that means for the wider network topology, and then calculate, do I need to change any of my paths? Do I need to change any of my best paths that I'm currently forwarding traffic on? Yes, okay, let's install that new route, that new routing information. No, okay, continue doing whatever we've done, but we've still gone and checked and we've made sure that nothing bad is going to happen, basically. It also allows us to have very highly scalable networks without a lot of overhead. You know, you take the example of, you know, a data center. If a data center was based on static routing alone, that would be a huge nightmare. You think about the likes of AWS, for example. They would have to have a whole army of network engineers constantly at their CLI typing in new management configuration for those static routes. And that's exactly why we have these dynamic protocols, which will learn new state and make those decisions for us. Now, those then dynamic protocols know that network state, but then how do they actually determine that the right path? Well, that's all based on some kind of metric. So that might be bandwidth, that might be hop count, it might be reliability or utilization. There's a wide range of different protocols which will do different things. So it really does depend on the specific use case. So just touching briefly on some specific examples to give you guys a little bit of a diagram with the specific pros and cons of the different things. So what I've got is 3 slides here, which are going to compare static protocols or static example on the left-hand side, this side, and a dynamic routing protocol on the right-hand side. And in this case, it's representing traffic flow. So in the case of static, if you want to move traffic from this R6 device, from this subnet, to this destination subnet on R1, then you're most likely going to implement some kind of static route pointing towards R4. R4 is going to point towards R2, and R2 is probably going to point to R1. If you're sensible, you would have probably put in some maybe redundant paths here and there. So maybe you've added a redundant path via R6 to R5. Maybe you've added a redundant path via R6 to R5, and then so on and so forth. Obviously, the more redundant paths that you add in, the more state that you're adding to the network, the more static configuration that you've got to manage and understand whenever you want to make a change of any form. So that's the static representation. Realistically, you're probably going to only have one active path at any one time. The alternative is dynamic routing protocols. Now, normal operation of a dynamic routing protocol is that you will set it up, you'll define some neighbors or some interfaces which might have neighbors behind them, and the routing protocols go away and try and understand that network state. They'll understand the bandwidths, they'll understand the metrics. And as a result, R6 will have a concept and an understanding of the whole network. Because of that, it can calculate all the relevant best paths or paths in general. And it can say, okay, this path is the best path. This is how I get to R1 with the shortest or lowest metric. And in some cases, in the case of this example here, because we've got a range of equal cost paths, so To get from R6 to R1, we can go from R6, R4, R2, R1 for a cost of 30. We can go to R4 to R3 to R1, or we can go to R5 to R2 to R1, all with a cost of 30. And so what the routing protocol is going to do in the background in this case is it's going to install all those 4 paths, and it's going to say, okay, the metric across all of those 4 paths is equal, let's load balance. And so what you end up with is, instead of one single path potentially, or multiple paths requiring multiple levels of configuration, static configuration, and administration overhead, you then get a very nicely clean and load balanced network and traffic flows. Now, obviously, there's some downsides to load balancing. That's out the scope of this talk. But yeah, that is one advantage with dynamic stuff. And obviously, there are drawbacks. Load balancing can go wrong in some situations where you've got very what are called very fat flows, where they are multiple gig in size compared to some other flow which might be kilobytes per second, for example. Anyway, moving on to the next example, and that's a link failure. Well, in the case of a static route on R6, that static route might be pointing out only towards R4. If that's the case, well, R6's interface is down. So it receives traffic that should be going out of this interface. Well, it can't now forward it. So R6, unless it has some redundant network state, is going to just drop that traffic. And at that point, you've got some kind of service impact. Till someone comes along and notices that the interface is down, actually logs into the device and configures new state. That's obviously going to take some time. It's not going to be a case of a few minutes or a few seconds. It's going to potentially be an hour to maybe a few days, depending on your network, the implementation, the support behind it. The alternative is the dynamic protocols on this side, which will understand the state in its network and be able to reroute the traffic based on that. In this example, we're emulating a failure on the link between R4 and R6, which was previously one of the forwarding paths. Let's say it was the main forwarding path and we weren't doing the concept of load balancing. If that then fails, R6 sees that instantly because it's directly connected and says, okay, I need an alternative path straight away. The alternative path can be via R5. But what it's going to do in the background is going to calculate and it's going to understand the network state. Now something has changed and it's going to build its potential tree of alternative paths. As a result, it'll then pick the lowest cost or tie break against something and pick that specific path. In some protocols, it already does this preemptively and says, okay, my backup path is via this interface, via this specific path. So obviously, yet again, it's a benefit over static. In the case of static, maybe you've got some service impact for a few minutes, a few hours, a few days, depending. In the case of dynamic protocols, you're flipping over straight away within a matter of seconds, usually. Obviously, yet again, depends on the protocol. In some cases, in some protocols, that detection of failure, certainly more upstream, can take a few seconds, it can take a few minutes, depending on the protocol and the size of routing information. Moving on to the final example, and that's where maybe something has changed with the cost or the bandwidth or the metric of this link between R6 and R4. So we can maybe imagine this as these 10 these links of cost 10 are potentially 2 10 gig links combined to make 20 gig capacity on each of these links. Their cost is then matched to, let's say, 10. But in the case of this link down here, we've just lost half of our capacity. So the cost increases, it doubles because we've just lost half of that capacity. Because of that, in a dynamic protocol world, yet again, the router sees that state change. It does a path calculation to understand the network state, and it will then recalculate the best path. Maybe the best path is still via this interface,
but because of that state change, it's still going to process the updated cost and try and make sure that it is still using the best path. In this case, because we know that we've got a lower cost path, we're going to follow that cost, that lower cost path all the way up to our destination. In the case of a static route, that static route won't have any idea that something has happened to the link. If the link is still there, it's still going to forward traffic. Now, there are some certain implementations where you can monitor a path and trigger a specific static route to be implemented if that condition against that path is valid. That's one way to potentially get around this, but otherwise, usually with inside normal operation of a static route, it won't take into consideration these state changes, whether that be a link down or whether that be a metric change. So that's just some practical examples to give you guys a bit of a more solid understanding on the difference between those static and dynamic routing protocols. Maybe it's a little bit too much, but hopefully it really hits home actually what the differences are there. As I alluded to before, we've got this concept of routing tables, and that routing table might contain multiple or duplicate pieces of routing information that match your destination. So the best way to think about a routing table is, I'm going to come back to that analogy of driving to a place and you're coming up to a roundabout. So let's say we came up to a roundabout and we're going on our way to Manchester, and we have signs that say, oh well, that exit for Manchester, that exit for Birmingham, that exit for London, for example. You take the exit towards towards Manchester. Or when you get closer to Manchester, well, then you're going to have more specific signs, which may say, well, this exit towards the airport in Manchester, this exit towards city centre of Manchester, for example. And that's where this concept of this more specific, these more specific subnets comes into play. As I was discussing before, right at that intro, we've got this concept of a subnet mask or a subnet. And the more specific that subnet is, the less potential end hosts that you have inside that subnet. So in the case of a /18, it's like 16,000 potential end hosts. In the case of a /24, it's around 250. That's less ambiguous and it's more specific. So there's more probability that if you follow that more specific route that you're going to actually get closer to your end host. So that's why we have those more specific routes. And so that's the first decision that a router takes. It looks at all of its routing information and it sees what routing information actually matches this destination IP that I'm trying to reach. In this case, we've got a routing table and maybe it's been summarized to only match those specific routing entries that match the destination. And so we've got a default route that will match on everything. That's a good example of how we can provide internet access. A network administrator doesn't necessarily know all of the different subnets that their end users might need to reach. So we install what's called a default route so that we can match on anything, regardless of whether we've got the routing state or not. If we don't have the routing state, well, we match on that default route, and then it goes to some kind of central location or more core location, which might have a better chance of understanding that packet and knowing where it needs to be sent, in what direction it needs to be sent. Now, in this situation, let's imagine that we're trying to reach this subnet, and we have this specific routing table. We look through it and we see, okay, this default route, yeah, it matches, but it's not that specific. There's a huge, wide range of addresses that match this /0, 4 million or 4 billion, I can't remember the exact number, but around 4 billion, I believe, addresses, which would be inside a standard IPv4 address. So sure, it matches, but it's not specific whatsoever. We have a /16, cool. That's good. It's more specific, but it's still
65,000 potential end hosts that we're representing with that entry. So it's not too specific, but it's better than just 4 billion. We then have 2/24s. Well, that's more specific even further. That's around 250 hosts that we could potentially be hitting with that destination. So the routing table, the router will look through that routing table and say, what's the most specific information? Well, it's these two here. They both have the same subnet, and they both have the same subnet mask, that /24, which means they represent the same end hosts. So, okay, we've got two tying routing informations. We can't obviously use both because they're going out of two separate interfaces. One's going towards R4 and one is going towards R5. So what we do is on the routers, we determine some kind of priority list. And that priority list is linked to the specific protocol or implementation on how we've got that routing information. So in this situation, we've got two pieces of routing information. One is from a static implementation, and one is from what's called OSPF. That's a dynamic routing protocol. If you don't know what OSPF is and you're finding all of these talks very interesting, I've done a talk specifically on OSPF, which is a more technical introduction into it. Apparently it's a very good talk, so if you are interested, go and take a look. But otherwise, from the router's point of view, a static route is something that has been explicitly configured to it. And as a result, it knows it to be relatively or pretty well defined and reliable. That's the specific thing. It needs to be reliable. Now, sure, OSPF isn't full of bugs, but there's a chance that something could be wrong with an OSPF route. I'm not saying it is. That's not the intention of OSPF. But obviously, sometimes mistakes are made. Sometimes there is bad state in a network. And so what this selection process does is it looks for routing information that is more reliable than something else. And so in this case, I've given the example of static and OSPF information. And in the case of that, well, static information is more reliable than dynamic information, or the case of this OSPF. And now for each different vendor, there is a different list, and it's slightly different depending on those different vendors. That list also, router by router, can be managed. You can change your routing information for static implementations to be, less reliable or less preferred compared to other protocol routing information. So that's how a routing table would work. That's how a router would work, looking at its routing table to define the forwarding path. In this case, because it's sending towards this subnet, it matches on the most specific, which is these two entries. It looks at the most reliable entry. And in this situation, it is this one here, which is out of Ethernet 2. It then forwards the traffic down that path after doing anything else that the router needs to do before it forwards traffic. So that's how we deal with a routing table. Now, obviously, in the case of dynamic protocols, we mentioned that the selection of a path is based on a best cost or best path to that destination. And there's a lot of ways that you can do that, and it does depend on the routing protocol that you choose. So this is where it moves more from fundamentals into potential actual implementation. But I think it's good to give this a bit of an example and understanding. So you've got a protocol called OSPF that is open shortest path first, and it runs on a specific algorithm called Dijkstra's algorithm. And I've referenced here down at the bottom a specific YouTube video. I'll link that in the description, and I'll also send it to the guys who are watching this. That YouTube video is a really good example and explanation of Dijkstra's algorithm. Now, I could spend another 30 minutes going on about what that is, how it works, and I would probably make a mistake somewhere. So that video is a really good explanation of that algorithm without me stumbling my words and getting it wrong. So if you're interested in understanding actually how we actually calculate those different paths and the actual best path, give that a watch, and it'll be well worth your time. But anyway,
What are those metrics based on? Well, OSPF is based on bandwidth. So that is the bandwidth, the raw bandwidth of those interfaces. So whether it's a 10 gig link or whether it's a 1 gig link or whether it's 100 meg, for example. So it'll rate the higher bandwidth links better than the lower bandwidth links. So it'll prefer to go down a 100 gig link rather than a 1 gig link, for example. Now, there are some few caveats to that, and yet again, go and check out the OSPF video if you're really interested, where I talk a little bit more about that. There's then a protocol called RIP, Routing Information Protocol, and that is based on just physical hops. So how many hops between the source and destination are there? And that is layer 3 hops, just to be very clear. So hop from one router to another, and if I actually go forward one, this is a quick example. No. Okay, I'll go back to a proper diagram. So you've got here R6, you want to get to R1, well, 1 hop, 2 hop, 3 hops. So to get from R6 to R1, you're going R4, 1 hop, to R2, another hop, and to R1, another hop. Metric of 3 in that situation. So very, very simple. EIGRP is by default based on bandwidth and delay, but EIGRP is Cisco proprietary. And there's a few reasons behind it, and there's reasons why people hate it, because it is only Cisco only. But it also does have some really interesting functionality there, and it does also have some extra metric values that you can base your costs on. So you can consider load or utilization of a link, you can consider reliability, and you can consider MTU, maximum transmission unit. And all of those different values, including bandwidth and delay, can be tweaked to have a higher preference in the metric calculation. So if you want to have reliability be more important in metric calculation than bandwidth, for example, then you can tweak the calculation in the back end to say, well, consider reliability a lot more than bandwidth, for example. So that's EIGRP. There is then BGP, and BGP is a little bit out of scope, definitely, to talk about on this this topic. But yet again, it's another one of those topics where I've done a video on them. So go and check that out if you want. Very, very interesting protocol for very large scale deployments. But it's based on hops between what's called an ASN, and an ASN is an autonomous system. So you can imagine that as BT, as Virgin Media, as AWS or Microsoft or DigitalOcean, for example. Those themselves are autonomous systems. And so if you pass through one of those autonomous systems, that's 1 hop. Now, the fancy bit about BGP is there's a bunch of extra little bits added on, and there are there's what's called attributes, and those attributes can actually change the routing decision. So while the absolute bare bones of BGP is based on number of hops, there's a bunch of attributes to that routing information that can make a difference based on if you're tied for hops, you can select a path based on something else. Yet again, watch the video that I've done on it. It goes into a little bit more detail on what I'm talking about. But yeah, as I mentioned, there's plenty of algorithms that can be used for these selections. Dijkstra is one of the most popular, I would say, and it's probably the best one to really understand this topic with. So one of the final things to touch on is split horizon. And this is really important when you're talking about routing information and sharing that routing information across the network. Imagine a world without split horizon. What that means is when we're sharing network state across your network, let's say R4 has some network state that it's learned, this prefix here, or this subnet, I should say. R4 is going to advertise that up its network from towards R3, towards R2, and towards R1. Now, before split horizon, these routers would be relatively dumb, and they would say, okay, I've got this new state, I've processed that, let me share it with my neighbors. And what will end up happening is it'll send it, yeah, sure, it'll send it to R2, but it will also try and send it to R4. Obviously, R4 has the original state, so there's no need for R4 to learn that. But in the case of pre-split horizon, without split horizon, what R4 is going to see is it's going to see that routing information as something new because R3 has originated it. R4 is going to learn it, but obviously never use it because it's already got this original routing information state, so it's not preferred. Now, if that routing information, that original routing information disappears from R4, so let's say a link is disconnected and you're no longer seeing this subnet, well, then R4 doesn't have the original details. And R4 only has the information that R3 sent it. In that situation, that's going to be a bad state. Because R4, if it receives a packet that is destined towards this network, what it's going to do is it's going to look at that stale state that R3 had sent it and say, well, R3 has the routing information, send it towards R3. R3 is going to see that and it's going to say, well, actually the cost to that subnet is cheaper or lower via R4. So I'll send it to R4. R4 knows what to do. It knows best. R4 is going to receive it, see that it only has that stale state that it learned from R3 and send it on to R3, so on and so forth. You end up then in a loop, an infinite loop. So what split horizon does is it says, and it implements the rule that if you're learning network state from a neighbor, don't then go and forward that learned network state back to that neighbor that you've just received it from. And what that does is that stops, in this case, it stops R3 advertising the state that R4 has just sent to it. As a result, if this network state is lost, well, then R4 doesn't have any state. Now, that's great for R4, but in that situation, R3 still has that state. It still has that state cached in some sense because it doesn't know that the original source routing information has disappeared from the network. So it still thinks that R4 is the next best path to reach that destination subnet. As a result, if it receives traffic destined towards that, it's going to forward it down to R4, and R4 is going to be like, I don't know, drop it on the floor. And then you're starting to see service impact. Sure, maybe you have alternative routing information that means that you can forward it on to maybe a default route. But obviously, there's a chance that passing via R4 is going to be suboptimal. And so obviously you want to prevent that. So one extra thing with a second functionality that Split Horizon provides is when it knows that this original state has been lost, it actually poisons the route down the network path to say, okay, I sent you this routing information previously, but actually now it's no longer valid. There's many ways that you can actually do that, and it depends on the routing protocol that you use. But that could be as simple as sending a message saying, this routing information is no longer valid, delete it from your table. And so the poison message will be sent to R3. R3 will then delete its state. R3 will pass it on to R2. It will delete its state. R1 will do the same, so on and so forth. As a result, you no longer see that state within inside the network, so no one can suboptimally send traffic. And so that's Split Horizon in a nutshell. It's basically making sure that the network state stays fresh, effectively. And when you remove network state from a network, it is actually removed, and it isn't relying on some stale state in the network. Obviously, depending on then the protocol that you select, whether that be maybe OSPF or EIGRP or BGP or RIP, there's different implementations, and there's different things that also enable removing stale routing information, things like timers, for example. But yet again, a little bit too much detail for this talk. Finally, just to finish off, just to give you some kind of understanding of those different protocols and where they might be useful. So you've got static routing, very good, as I mentioned, for small, simple networks, but it doesn't scale whatsoever, and if it does, well, you're going to be in for a headache trying to manage it or trying to make any additions. If you have even just the slightest bit of redundancy, well, then you're going to have to manage multiple static routes to multiple destinations to multiple different links. That does not work in the long term. It's also not dynamic in such a sense that, if a link goes down, well, that static route is still configured, so it could still be used. There's then dynamic protocols. So you've got RIP, as I mentioned before. That's an old school protocol and should work on a range of devices. Just to anecdote that, I think one of my home routers actually supports RIP, like a Virgin Home Hub, for example, or one of these kind of like routers that you can get off the shelf. They support RIP, and that just shows how kind of old and how easy it is to run those protocols, that these very simple devices can even link up with a RIP domain. But obviously it's very limited in its operation. It's a limited metric, so it's only based on some kind of hop count, which is never really good if you've got a wide range of network links. If you've got potential for 100 gigs of links versus like 100 megabytes or a gig or even kilobytes of data, in the case of serial links. So while RIP is good in theory and in very simple topologies where you know exactly what you have and it's very consistent, realistically, it's never the optimal solution unless you have nothing else to select. You then have OSPF. Well, OSPF is good, is a genuinely good, solid selection. It works from very small scale to very large scale. So you can use it in those small office environments, but you could also use them in those big hyperscale, data center environments. They start to then get a little bit buggy in those situations because you've got so much network state. And yet again, go and watch the OSPF video if you're really interested. It gives you a little bit more insight into why I say that maybe when you get to the bigger scales, it doesn't work too well. But it has a lot of control options within limits, and it's very good for operationally understanding what is going on and very clearly seeing the state within inside the network. You then have EIGRP. As I mentioned before, it is Cisco only, which is a pain, but it is very similar to OSPF. Now, it does have some very specific functionalities that others don't. So, you can base your metrics on different values like bandwidth and like reliability. That is unique to EIGRP. There aren't any other protocols that I know of personally that do that, or at least there aren't any well-known protocols that I know of that do that. It also has the ability to flip between a primary path and effectively a pre-calculated backup path, which yet again is a really nice functionality if you want quick failover. And then finally, you have BGP, which is really the big boys protocol. It doesn't stand for that. It stands for Border Gateway Protocol, and it is usually used for those hyperscale networks where you need really granular control of your routing information and how you flood that across and how you scope it across a network. BGP is the thing that runs the internet effectively, so you can understand the scale that it's working at. Now, it can be used internally. There's nothing stopping us from, using BGP in an office environment, but it just doesn't work properly, and it's not as easy to administer in those smaller networks. Things like OSPF are much easier to use in a smaller local network. So that's a bit of an insight into these into layer 3 routing and static versus dynamic, and some of the options that you have when you're dealing with these kind of routing protocols. So I hope that's very interesting. And if you obviously want more detail on some of those protocols, as I mentioned, I've done some videos on OSPF and BGP, so feel free to go and check those out. Otherwise, thanks for watching, and I'll talk to you later.